Okay, hello, welcome to today's lecture. We're still on chapter 7. We're going to continue chapter 7 before starting 7.5. We're going to go over 7.4, what we learned last lecture. So in 7.4, review. We look at if we have a rational expression, px divided by qx, we have to look at the degree of the numerator and the degree on the denominator. What's the degree of px? What's the degree of qx? Then, based on the degrees and the relation between degrees, we're going to either do the long division or using the composition of fractions. The very first case that you had was the degree of your numerator was greater than or equal to the degree of your denominator. What we're going to do in this case, first we're going to do long division. Px divided by qx. The second part, the second strategy was, what if the degree of the numerator is less than the degree of the denominator? The degree of px is less than the degree of qx. Then we look at the denominator, qx. Look at qx. If qx is the product of linear terms, linear term 1 times linear term 2 times linear term 3, and so on, and these linear terms are different from each other. So let us use linear term 1, linear term 2, linear term 3. Then we separate px over qx using the composition of fractions. Here you write a over linear term, the first linear term, plus b, the second linear term, and so on. Then you start solving for coefficients a, b, c, and so on. This is your very first case when the degree of the numerator is less than the degree of the denominator. What if qx is the multiple of the same linear term? So if qx is linear term 1 times linear term 1 times linear term 2, and so on. So as you can see, the first linear term is repeated. In this case, px divided by qx can be written as a over linear term 1 plus b over linear term 1 squared, because it's repeated twice, plus c over linear term 2 plus the rest. So based on the composition of your denominator, you try to form these new fractions. And we also learned that if qx is the product of linear terms and quadratic terms, if it is linear term times quadratic term, then px over qx can be written as, you get your linear term a divided by your linear term plus, now that you have a quadratic term which you cannot break down into the product of linear terms, on your numerator you have bx plus c. You get a linear term divided by your quadratic term. And that's how you continue to break down the integral and write it in simpler format so you can solve it. Very well. In 7.5, 5, we're going to check to see which technique works for an integral that we have. So first of all, the table of integrals. Let us just wrap up everything that we learned, different techniques and integrations here, different formulas. The first one that we learned was the integral of x to the n dx. If you have a power function, then the integral is x to n plus 1 over n plus 1 plus constant of integration. If you have the integral of dx over x, is going to be ln of x. So let me write it down here, or let us write this guy a little bit further to the other side. We need more space. Ln of absolute value of x plus c. Then you learn that if you have the integral of e to the x dx, it's going to be e to the x plus c. And you can generalize the idea. If you have the integral of e raised to ax dx, it is e to ax divided by a plus c. If you have the integral of v to the x dx, this is e to the x divided by ln of v plus constant of integration. If you have integral of sine x dx, it's going to be negative cosine x plus constant of integration. And you can generalize the idea. If you have the integral of sine ax dx, it's going to be negative 1 over a cosine ax plus c. If you have integral of cosine x dx, this is equal to sine x plus c. And of course, you can always use substitution. Integral of cosine ax dx is 1 over a sine ax plus c. Next, integral of secant squared dx is tangent, and integral of cosecant squared x dx is negative cotangent x plus constant of integration. Then you learned about the integral of secant times tangent x dx, which is equal to secant x. The integral of cosecant x cotangent x dx is minus cosecant x plus constant of integration. The integral of secant itself, secant x dx, is going to be ln of secant, absolute value of secant, plus tangent x plus c, and the integral of cosecant x dx is going to be ln of absolute value of cosecant x minus cotangent x plus constant of integration. The integral of tangent x dx is equal to ln of secant x plus c, and the integral of cotangent x dx is going to be ln of sine, absolute value of sine x plus constant of integration. Very well. If you have the integral of dx over x squared plus a squared, this is equal to 1 over a inverse tangent of x over a plus c. And if you have the integral of dx divided by square root of a squared minus x squared. This is equal to inverse sine x over a plus constant of integration. Let's go over some examples to feel comfortable about taking the integral. So we're still on page 1. So for example, the first example says, hey, find the integral of square root of x times 1 plus square root of x dx. Okay, there you go. We all know that if we have the nth root of x to the m, this is equal to x raised to m over n, and this is just the format of integral of x to the n dx. If you have an exponent, you get x to n plus 1 divided by n plus 1 plus constant of integration. So first, I'm going to distribute square root of x into parentheses. So distribute square root of x into parentheses. We get integral of square root of x plus square root of x times square root of x dx. This is equal to integral of square root of x plus square root of x times square root of x is just x dx. So square root of x times square root of x is square root of x squared, which is x. Very well. Square root of x is x to a half. So this is the integral x raised to a half plus x to the first power dx, which is equal to x raised to a half plus 1 divided by a half plus 1 plus x squared divided by 2 plus c. So if you simplify this, a half plus 1 gives you 3 halves. You get 2 thirds x raised to 3 halves plus x squared over 2 plus constant of integration. Next example. Now suppose you have the integral of tangent theta divided by secant squared theta d theta. Okay, perfect. I have tangent, I have secant. Remember that secant of theta is equal to 1 over cosine theta. So you have 1 divided by secant squared. This is equal to integral of tangent theta 1 over secant squared, which is cosine squared of theta. 1 over secant is cosine. Very well. So what is tangent? I know tangent is equal to sine over cosine theta and time cosine squared theta d theta. So of course I can simplify this guy. I can say that, hey, I have cosine and I can get rid of one of the exponents here. Here you have the integral of sine theta times cosine theta d theta. Okay, I have sine, I have cosine next to it. What's the meaning of that? It means that you can quickly use u sum. U sum. So let u be sine, U is your sine, du is cosine theta d theta. This is equal to the integral of u du, which is equal to a half u squared plus c. Our original integral is in theta, so we cannot leave it as u. We have to rewrite it using the exact same variable that we have, theta. So here we get a half sine theta squared plus c, and this can be written as a half sine squared theta plus c. Again, remember that sine theta to the second power is sine theta times sine theta, which is sine squared theta, which is different from sine theta squared. These two are different from each other. Know the difference between these. Here you multiply sine by sine, you get sine squared. Here you are just multiplying theta by itself. We are still on page 1. So now the question says, you have this integral. Find the integral of x divided by x squared minus 1 dx. Very well. So first you look at this integral and say, hey, I have a rational expression. You might say, I can write it as px divided by qx, and then I'm going to decompose this into a over x minus 1 plus b over x plus 1, and so on. Decomposition of fractions. So I say, take a look at your denominator. Let us see if we can use a different method that we learned before proceeding using the decomposition of fractions. I say, hey, on my denominator, I have x squared minus 1. So if I use u sub, my u is going to be x squared minus 1, and my du, the derivative, is equal to 2x dx. 2x dx. And if you look at your numerator, you already have your x. So if you multiply the numerator by 2 and divide it by 2, you can actually have du divided by u, which is ln of absolute value of. So this is a half integral du over u, which is a half ln of absolute value of u plus c, which is a half ln of absolute value of x squared minus 1 plus c. So before start using the decomposition of fractions, see if you have the derivative of your denominator on your numerator or not. Sometimes it's easier to just use u sub method. Okay, let us move on to page 2. Page 2. In page 2, you have this type of integrals. You have integral dx divided by 1 minus cosine x. Very well. Okay. Guys, here you have dx divided by 1 minus cosine x. So what I'm going to do, I'm going to multiply both the numerator and the denominator by the conjugate of 1 plus cosine x. The conjugate of 1 minus cosine x, which is 1 plus cosine x. So when you have an integral like dx over 1 minus cosine x, dx over 1 plus cosine x, dx over 1 minus sine x, dx over 1 plus cosine x, you can always multiply the numerator, the denominator, by the conjugate of your denominator, which is just the difference between the operations, the opposite operations that you're using. Okay, this integral is now dx divided by 1 minus cosine x. I'm multiplying both the numerator and the denominator. 1 plus cosine x divided by 1 plus cosine x. Okay. Now I have a new numerator. My numerator is equal to integral 1 plus cosine x dx. My denominator, on the other hand, if you multiply 1 by 1 by cosine x, negative cosine x by 1, negative cosine x by negative by cosine x, is minus cosine squared x. You can cancel out the opposite terms. What do you get? You get the integral of 1 plus cosine x dx divided by 1 minus cosine squared. 1 minus cosine squared of x. 1 minus cosine squared, you already know that is sine squared. This is equal to the integral of 1 plus cosine x divided by sine squared x dx. Okay. Now we can handle this integral. Why is that? This is 1 over sine squared plus cosine x over sine squared. So you can rewrite this integral as the integral of 1 over sine squared plus cosine x divided by sine x times sine x dx. This integral is 1 over sine squared, which is equal to the integral of cosecant squared of x. And this integral is cotangent times cosecant x dx. The integral of cosecant squared, if you remember the table, is equal to negative cotangent x, and the integral of cotangent cosecant is equal to negative cosecant of x plus constant of integration.
Professor?
Okay, you are on page 3. We're going to continue the examples. Where now here you have the integral of tangent. My tangent has exponent 3, x divided by cosine to the third of x dx. Okay, so when you have tangents, you have cosecant, try to simplify it as much as you can. So try to simplify. How do we simplify that? You know that tangent is sine over cosine. So here you get the integral of sine over cosine to the third, this is my tangent, times 1 over cosine to the third of x dx. Very well. This integral can be written as the integral of sine to the third of x divided by cosine to the third of x times 1 over cosine to the third of x dx. Note that on your denominator, you have cosine and cosine. So you have a 1 cosine and add the exponents. So you get the integral of sine to the third of x divided by cosine to the 6th of x dx. Very well.
I have a question. Is it supposed to be 9 to the 9?
Perfect. Now you might say, very well. I have sine, I have cosine. So I can use u sub somehow. If I take u to be cosine, du is sine. The only problem that you have is the exponent of sine. So somehow you have to get rid of this exponent 3. So to use u sub where u equals to cosine x, we try to simplify the numerator. Okay, your integral is equal to the integral sine to the third. What is sine to the third? It is sine squared times the sine. Okay, very well. I'm hopeful here because I have sine squared. I can convert sine squared into cosine. We're going to see later. Cosine to the 6th of x, and sine squared can be written as 1 minus cosine squared. Perfect. Sine x dx divided by cosine to the 6th of x. Perfect. We're almost done. So let u be cosine x, du is minus sine x dx. I have u, if I just multiply it by a negative sign, I'm done. Minus and minus. So here you get negative integral 1 minus u squared divided by u to the 6th du. This integral is super easy to handle. This is minus the integral 1 over u to the 6th minus u squared over u to the 6th du, which is equal to minus integral u to minus 6 minus u to negative 4 du, which is equal to, let's put the negative sign out here. You get u to negative 6. If you add 1, you get negative 5. So you have u to minus 5 over minus 5 minus u to negative 4 plus 1, negative 3, u to negative 3 divided by negative 3 plus constant of integration. So what is u? U is cosine of x. This is equal to minus negative 1 over 5 times cosine to the 5th of x plus 1 over 3 cosine to the third of x plus constant of integration. You can distribute the negative sign here. You get 1 over 5 times cosine to the fifth of x minus 1 over 3 cosine to the third of x plus constant of integration. Next example for you. Perfect. So now you have integral of e raised to square root of x dx. Very well. I have exponent square root of x. I know that if I have the integral of e to the x dx, this is equal to e to the x plus c. Guys, integral of e to square root of x dx is not equal to e to square root of x plus c. This is wrong. Be careful. So what I'm going to do instead, I'm going to use a substitution. I'm going to let t to be square root of x, then dt is equal to dx divided by 2 times square root of x. Okay. So my dx is equal to 2 times square root of x times dt. And since t is equal to square root of x, I'm going to replace that here. So my dx is nothing but 2t dt. So your integral is equal to the integral of e to t, and instead of dx, I have 2t dt. Okay, here you have e to t, 2t dt. How do we take this integral? We're going to apply integration by parts. Integration by parts. Okay, let us use our little table, u dv du and v. So since my goal is to reduce the exponent, I'm going to take 2t as my u. And dv is equal to et dt. So du is equal to 2 dt, and v is equal to the integral of et dt, which is et. So this integral is equal to uv 2t et minus integral v du 2 et dt, which is super easy to handle. This is 2t et minus 2 et plus constant of integration. Okay, let's get back to our integral. Our integral is in x, so we have to change these variables and write them in x. Okay, t is equal to square root of x, so this is equal to 2 square root of x e to square root of x minus 2 e raised to square root of x plus constant of integration. Let's move on to the next example, another integral. Very well. You have the integral of dx over x times square root of ln of x. Okay, so when you see ln of x, try to use u sub. ln of x, take this as u. Then du is equal to 1 over x times dx. Do I have 1 over x dx? Yes, I have it just right here. This integral can be written as integral of du divided by square root of u. Now I already know how to handle this integral because this is equal to the integral of du over u to a half, which is integral u to negative a half du, which is equal to u to negative a half plus 1 divided by negative a half plus 1 plus c, which is equal to u to positive a half divided by a half plus c, and this guy is equal to 2 times square root of u plus c, which eventually can be written as, since my u is ln of x, we can use this u and substitute this here. 2 times square root of ln of x plus constant of integration. One last example on this page. So here I have the integral of square root of 1 minus x divided by 1 plus x. All of them are inside the radical. Okay, perfect. What should I do here? When you have the square root of x plus a over x minus a, or x minus a over x plus a, multiply this by, flip this fraction and multiply by its radical. Okay. Then try to simplify as much as you can. Or better, you can use u sub or square root. So let u be the square root of 1 minus x divided by 1 plus x. So my du is equal to du. First of all, here you have a radical. You can write it as a half 1 minus x divided by 1 plus x raised to negative a half. And now you have to take the integral and take the derivative of the quantity inside the radical. This is equal to negative 1 times 1 plus x minus 1 minus x divided by 1 plus x squared dx. So du is equal to a half times 1 divided by 1 minus x, 1 plus x raised to positive a half. Let's simplify your numerator. This is equal to, multiply. This is equal to negative 1 minus x minus 1 plus x divided by 1 plus x squared times dx. So du is equal to a half 1 divided by 1 minus x, so you can write it this way, and just flip the whole thing, square root of 1 plus x over 1 minus x. And here you can simplify this, negative 2 divided by 1 plus x to the second power dx. Of course, we can simplify this more. You can combine these two, your denominators, 2 plus a half, which is 3 halves. You get 1 minus x times square root of 1 minus x. There you go. So as you can see, you get more complicated expressions here. So you might say, okay, I don't know how to deal with this. Is there any other method? Can I change this function into other format before doing any use of? So when you get to more complicated terms, expressions, stop for a bit, get back to your integral and think. Here you have square root of 1 minus x divided by 1 plus x. What if we multiply both the numerator and the denominator by square root of 1 minus x. Let's see. So here you have the integral square root of 1 minus x divided by square root of 1 plus x. I'm going to multiply both my numerator and my denominator by square root of 1 minus x. Why is that? Because I want to get rid of this radical on my numerator. So square root of 1 minus x divided by square root of 1 minus x dx. Okay? Here I get the integral square root of 1 minus x times square root of 1 minus x, which is 1 minus x. On my numerator, I got rid of square root. On the denominator, you get square root of 1 times 1, 1, 1 minus x, negative x plus 1, x minus x dx. Very well. Okay. Remember now, if you get back to your table that we taught at the beginning of this lecture, if you have square root of 1 minus x squared on the denominator, remember that we call the integral of dx over square root of 1 minus x squared is actually inverse sine. Inverse sine of x plus c. So this is a good sign. This is a good sign. So what I'm going to do, I'm going to rewrite this as the integral of 1 divided by square root of 1 minus x squared minus x divided by square root of 1 minus x squared dx. I already know this integral is inverse sine. So I'm dealing with this using the formula that I learned before. For this one, for the second one, we can easily use u sine. So this one is inverse sine x, and this one use u sine. Perfect. So u is equal to 1 minus x squared, du is equal to negative 2x dx. You already have your x, so just multiply by negative 2, divide by negative 2. This is equal to, so I'm going to write down the first integral as inverse sine of x. And here for the second integral, I have negative 1 over 2 integral minus 2x dx divided by square root of 1 minus x. So this is equal to inverse sine of x. I have plus a half integral of du over square root of u, which is u2 negative a half, which is equal to inverse sine of x plus a half. Negative a half plus 1, positive a half. You flip that, you get 2 times u2 a half plus c, which is equal to inverse sine of x plus square root of u. What is u? 1 minus x squared plus constant of integration.